Welcome to our introduction to binary outcomes and logistic regression. In many real-world problems, we encounter binary outcomes, situations with only two possible results. Examples include whether a patient survives a treatment, if a customer makes a purchase, or if an email is spam. Consider a healthcare scenario where we need to diagnose if a patient has diabetes. We collect various data points about the patient, such as age, BMI, blood glucose levels, and family history. Based on this data, we need to determine a binary outcome. Does the patient have diabetes or not? Logistic regression is a statistical method designed specifically for predicting the probability of binary outcomes. Unlike linear regression, logistic regression uses a sigmoid function to map any input to a probability between 0 and 1. This makes it ideal for binary classification problems where we need to predict one of two possible outcomes. Logistic regression is part of a broader machine learning workflow where we select and pre-process data, extract features, apply classification algorithms, and evaluate performance. The true value of logistic regression lies in turning predictions into actionable insights across various domains. In healthcare, it enables early disease detection, personalized treatment plans, and efficient resource allocation. In finance, it supports credit risk assessment, fraud detection, and customer retention strategies. Logistic regression transforms raw data into probability estimates, helping decision-makers take informed actions based on predicted outcomes. The logistic function, also known as the sigmoid function, is the mathematical foundation of logistic regression. It's characterized by its distinctive S-shaped curve, which maps any input value to a probability between 0 and 1. The equation for the sigmoid function is sigma of z equals 1 divided by 1 plus e to the negative z. When the input value z is very negative, the sigmoid function approaches 0. At z equals 0, the function equals exactly 0.5, which represents a 50% probability. And when z is very positive, the function approaches 1. Let's examine some key properties of the sigmoid function. The sigmoid function has a smooth S-shaped curve that gradually transitions between its extreme values. It's centered at the point 0, 0.5, and exhibits symmetry around this point. The shape of the sigmoid curve can be adjusted by parameters, changing how quickly it transitions from 0 to 1. In logistic regression, the input z is a linear combination of features weighted by coefficients. Let's understand the equation behind logistic regression. The logistic regression equation uses a sigmoid function to map any real-valued number to a probability between 0 and 1. The variable z represents the linear combination of all input features, each multiplied by its corresponding coefficient. Here we can see the sigmoid function. It has an S-shaped curve that maps any input value to a probability between 0 and 1. When z equals 0, the probability is exactly 0.5. As z increases, the probability approaches 1, and as z decreases, the probability approaches 0. Let's look at a practical example. Imagine we want to predict if a customer will make a purchase based on their age and income. If we have a 35-year-old customer with an income of $60,000 and our model coefficients are -3.5 for the intercept, 0.04 for age, and 0.00025 for income, we can calculate z as -3.5 plus 1.4 plus 1.5, which gives us -0.6. Now we can plug this z value into the sigmoid function. We get 1 divided by 1 plus e to the power of 0.6, which is approximately 0.35. This means there is approximately a 35% probability that this customer will make a purchase. In logistic regression, we often set a threshold of 0.5 to make a binary prediction. This threshold corresponds to z equals 0. Here we can see a visualization of a decision boundary. The line represents where z equals 0, or where the probability equals 0.5. This boundary separates the two classes. Points above the line have a higher probability of belonging to the orange class, while points below the line are more likely to belong to the blue class. To summarize, z transforms multiple input features into a single value. The sigmoid function then converts this z value into a probability between 0 and 1. By understanding how different values of z map to different probabilities, we can interpret and use our logistic regression model effectively. In logistic regression, the coefficients determine how predictors influence the probability of the outcome. The logistic regression equation uses coefficients beta 0, beta 1, and so on with a sigmoid function to calculate probabilities. Each coefficient has a specific role. Beta 0 is the intercept, representing the log odds when all predictors are 0. The other coefficients represent the effect of each predictor variable on the log odds of the outcome. These coefficients directly affect the shape and position of the sigmoid curve. When beta 0 increases, the entire curve shifts to the left, changing the threshold at which probabilities exceed 0.5. When beta 1 increases, the curve becomes steeper, making the transition from low to high probability more abrupt. The logit function is the logarithm of the odds ratio, and it forms the basis of logistic regression. It transforms probabilities, which are bounded between 0 and 1, into the entire real number line, from negative infinity to positive infinity. The logit function is the inverse of the sigmoid function, creating a critical relationship in logistic regression. This relationship allows us to model the log odds as a linear combination of predictors, connecting the nonlinear probability output to a linear equation. Understanding how to interpret coefficients is essential in logistic regression analysis. In the logistic model, coefficients tell us how changes in predictor variables affect the log odds of the outcome. A positive coefficient indicates that as the variable increases, both the odds and the probability of the event occurring increase. Conversely, a negative coefficient means that as the variable increases, both the odds and the probability of the event decrease. Let's examine a real-world example of logistic regression analyzing the relationship between smoking and mortality. In this example, the coefficient for smoking is positive 0.51. This means being a smoker increases the log odds of mortality by 0.51, indicating a higher probability of death compared to non-smokers. To summarize, when interpreting coefficients in logistic regression, remember these key points. A positive coefficient means increasing the variable increases the odds of the event. A negative coefficient means increasing the variable decreases those odds. The magnitude of the coefficient indicates the strength of the effect. For every 1 unit increase in the predictor variable, the log odds of the outcome change by the value of the coefficient. In logistic regression, the odds ratio is a key measure for interpreting results. First, let's understand what odds are. Odds are defined as the ratio of the probability of an event occurring to the probability of it not occurring. The odds ratio is calculated by comparing the odds of an event in two different groups. This table shows how we calculate the odds ratio from a 2x2 contingency table. Here's another example showing how to calculate the odds ratio. We divide the odds of exposure in cases by the odds of exposure in controls. Notice the cross-product formula, which gives us A is D over B is C. In logistic regression, the odds ratio for a predictor is calculated by exponentiating its coefficient beta. This gives us a measure of how the odds change when the predictor increases by 1 unit. When interpreting odds ratios, there are 3 key scenarios. An odds ratio of 1 means no association between the predictor and outcome. An odds ratio greater than 1 indicates the predictor increases the odds of the outcome. And an odds ratio less than 1 means the predictor decreases the odds. It's worth noting the relationship between odds ratio and relative risk. For rare outcomes, the odds ratio approximates the relative risk, as shown in this example. Here's a real-world example using a forest plot to visualize odds ratios. Each point shows how strongly different factors influence a particular behavior. Points to the right of the vertical line at 1 indicate increased odds, while points to the left indicate decreased odds. To summarize, the odds ratio is calculated by exponentiating the regression coefficient. An odds ratio of 1.5 means a 50% increase in the odds for each unit increase in the predictor. Conversely, an odds ratio of 0.75 means a 25% decrease in odds. These interpretations make logistic regression results actionable and meaningful. One of the critical assumptions in logistic regression is the independence of observations. Independence means that the outcome for one observation does not influence or depend on the outcome of another. Let's look at some examples. Independent events occur when one event doesn't affect the probability of another, like rolling dice multiple times. Dependent events, on the other hand, occur when the outcome of one event affects the probability of another. Mathematically, two events A and B are independent if the probability of their intersection equals the product of their individual probabilities. This means the occurrence of one event gives us no information about the occurrence of the other. Why is independence crucial for logistic regression? When this assumption is violated, statistical tests become invalid, standard errors may be underestimated, and the model makes overly confident predictions. Let's look at a practical example. In a randomized clinical trial, patients are typically randomly assigned to different treatment groups, making their observations independent. Independence is typically present in random samples, separate unrelated patients, and cross-sectional studies. Dependence, on the other hand, occurs in repeated measurements from the same subject, time series data, and clustered observations. These require special statistical techniques. Let's see how we might evaluate independence in real data. Here's a data set of movies where each data point represents a different film. This is a good example of independent observations, since the success of one movie generally doesn't directly influence another. To diagnose potential violations of independence, data scientists should examine data collection methods, plot residuals by observation order, and test for autocorrelation. While examining predictor relationships is important in logistic regression, as shown in these plots, independence between observations must be ensured through proper study design. Let's examine a key assumption in logistic regression: the absence of multicollinearity. Multicollinearity poses several challenges to regression models. It increases the variances of coefficient estimates, making them unstable and less reliable. This reduces their statistical significance and can seriously distort how we interpret the influence of individual variables. A correlation matrix helps us visualize relationships between variables. Strong correlations, shown in dark red or blue, indicate potential multicollinearity issues. Let's look at what multicollinearity actually means in practice. Here we can see a strong positive correlation between two predictor variables. When this happens, it becomes difficult to determine each variable's individual effect. The variance inflation factor, or VF, is the most common method for detecting multicollinearity. It measures how much the variance of an estimated regression coefficient increases due to collinearity with other predictors. VIF is calculated for each independent variable. The formula shown here uses R squared from a regression where the variable is predicted by all other independent variables. A higher VIF indicates stronger multicollinearity. But how do we interpret VIF values? A VIF of 1 means no correlation. Values between 1 and 5 suggest moderate correlation. Values between 5 and 10 indicate high correlation that may be problematic. And values above 10 signal severe multicollinearity that needs to be addressed. When multicollinearity is detected, there are several ways to address it. You can remove highly correlated variables, combine related variables into an index, apply regularization techniques like L1 or L2, increase your sample size, or use dimensionality reduction methods like principal component analysis. It's important to note that standard diagnostic plots like these might not always reveal multicollinearity problems. The model can appear to fit well even when multicollinearity is present, which is why calculating VIF values is essential for thorough model checking. To summarize, multicollinearity violates the assumption of independent predictors in logistic regression. While it may not affect overall prediction accuracy, it distorts coefficient estimates and their interpretation. Always check for multicollinearity using VIF when building your regression models. For logistic regression to produce valid results, the absence of multicollinearity is crucial for accurate interpretation of individual variable effects. The Hosmer-Lemeshow test is a statistical method for assessing the goodness of fit in logistic regression models. This test specifically examines how well the predicted probabilities match the observed outcomes. The test works by first grouping observations, typically into 10 equal-sized groups or deciles, based on their predicted probabilities. It then calculates a chi-square statistic to measure the discrepancy between observed and expected values. To perform the test, we first sort all observations based on their predicted probabilities from lowest to highest risk. We then divide these sorted observations into equal-sized groups, typically 10 groups or deciles. For each group, we count the number of observed events, which is simply how many positive outcomes occurred in that group. We also calculate the expected events, which is the sum of all predicted probabilities for observations in that group. The Hosmer-Lemeshow test statistic is calculated using a formula that compares observed and expected frequencies across all groups. The resulting test statistic follows a chi-square distribution with degrees of freedom equal to the number of groups minus 2. The null hypothesis is that the model fits the data well, meaning there's no significant difference between observed and expected values. If the p-value is greater than 0.05, we fail to reject the null hypothesis, suggesting the model has good fit. But if the p-value is less than 0.05, we reject the null hypothesis, indicating the model has poor fit. It's important to note that the Hosmer-Lemeshow test has limitations. A non-significant test result only indicates the model fits in the specific way measured by this test. Discrimination is a critical metric in evaluating logistic regression models. It measures the model's ability to correctly order risks and distinguish between observations with different outcomes. A model with good discrimination can effectively separate positive and negative cases based on their predicted probabilities. In contrast, a model with poor discrimination has significant overlap between positive and negative cases, making it difficult to distinguish between them. The Receiver Operating Characteristic Curve, or ROC curve, is a widely used metric to evaluate model discrimination. The ROC curve plots the true positive rate against the false positive rate at different threshold settings. The area under the ROC curve, or AUC, quantifies the model's discrimination ability. AUC ranges from 0.5, which indicates no discrimination ability, equivalent to random guessing, to 1.0, which represents perfect discrimination. When evaluating a logistic regression model, the AUC value helps us interpret the model's discriminative power. AUC values range from excellent discrimination above 0.9 to failed discrimination below 0.6. In real-world applications, models with strong discrimination ability can effectively identify patterns and measure different types of inequalities, making them valuable tools for decision-making. To summarize, discrimination is a crucial aspect of model evaluation that measures how well the model distinguishes between different outcomes. The ROC curve and AUC are powerful tools for assessing discrimination, with higher AUC values indicating better performance. A model with strong discrimination ability provides reliable risk predictions, which is essential for making informed decisions. L2, or ridge regularization, adds a penalty term to control model complexity and prevent overfitting in logistic regression models. The mathematical formulation adds a penalty term to the negative log likelihood function. This penalty is the sum of squared coefficients multiplied by a regularization parameter lambda. L2 regularization shrinks coefficients proportionally towards 0 without eliminating them completely. Larger coefficients face greater penalties, and this approach helps with multicollinearity by balancing the influence of correlated features. This visualization shows how L2 regularization works geometrically. The red ellipses represent the contours of the likelihood function, while the teal circle represents the L2 constraint. The optimal coefficient values are found where these two regions intersect. The lambda parameter controls the strength of regularization. Small lambda values result in minimal regularization, while large values lead to stronger coefficient shrinkage. The optimal lambda is typically determined using cross-validation. This graph illustrates how lambda affects the bias-variance trade-off. As lambda increases, variance decreases while bias increases. The optimal lambda minimizes the test error shown by the black curve. Let's compare L2 ridge regularization with L1 lasso regularization. Ridge uses squared coefficients, which shrinks all coefficients towards zero, making it ideal when all features matter. Lasso, in contrast, can shrink coefficients to exactly zero, making it useful for feature selection. This visualization shows coefficient paths as the regularization strength varies. Each line represents a different coefficient. In ridge regularization, coefficients are reduced proportionally, but typically don't reach exactly zero. The key takeaway is that L2 ridge regularization helps prevent overfitting by shrinking coefficients proportionally towards zero, and it works particularly well when dealing with correlated features. Logistic regression is widely used in marketing to predict customer behavior. Marketing teams follow a structured data science workflow when building predictive models. Let's explore specific marketing applications of logistic regression. E-commerce businesses use logistic regression to analyze and predict conversion rates throughout the customer journey. Logistic regression helps marketers predict which market segment a customer belongs to, enabling targeted campaigns. The model calculates the probability of a customer belonging to a specific segment based on their attributes. Marketers apply logistic regression at each stage of the customer acquisition funnel to predict conversion probabilities. This helps marketers predict transitions between funnel stages, identify valuable channels, and optimize marketing spend. Gaming companies use logistic regression to predict which players will make in-game purchases. Key predictive features include player activity metrics, game progress, social connections, and prior purchase history. The model reveals that previous purchase behavior is the strongest predictor of future in-game purchases. Marketing teams use logistic regression to predict where customers fall on the innovation adoption curve. The sigmoid curve of logistic regression perfectly models the probability of adoption based on customer attributes. Logistic regression has found powerful applications in the legal field, transforming how legal professionals analyze data and make predictions. Case outcome prediction systems use logistic regression to analyze historical legal data and estimate the probability of success for new cases. These models analyze features such as historical case data, identify patterns in judicial decisions, and calculate the probability of case success, with accuracy typically ranging from 70 to 85%. For example, in an intellectual property case, the model might predict a 76% chance of a favorable ruling based on key variables like the judge's prior rulings, case precedents, jurisdiction trends, and motion success rates. Contract risk assessment uses logistic regression to identify potentially problematic clauses and conditions in legal agreements. The model calculates a risk score based on various contract features, using the same sigmoid function we've seen in logistic regression. This technology identifies high-risk contract clauses, automates the due diligence process, and has been shown to reduce legal review time by up to 60%. Compliance monitoring systems leverage logistic regression to predict potential regulatory violations before they occur. These systems provide key applications, including regulatory violation prediction, real-time risk flagging, and compliance workflow optimization. Organizations implementing these predictive compliance systems have reported a 35% reduction in compliance incidents and 42% faster response to regulatory changes. When implementing logistic regression for legal applications, a typical model might look like this simplified code example. Successful implementation requires careful feature selection, regular model retraining, ethical review to prevent bias, and integration with domain expert knowledge. Data scaling is a critical pre-processing step in logistic regression that transforms features to a similar range. When features have drastically different scales, it can cause several problems for model training. Without scaling, features with larger ranges dominate the learning process, while smaller scale features barely contribute to model updates. Logistic regression models are typically trained using gradient descent to minimize a cost function. Data scaling dramatically affects how quickly this optimization algorithm converges to the optimal solution. Several common methods exist for scaling data. Min-max scaling transforms features to a 0 to 1 range. Standardization transforms features to have zero mean and unit variance, which is particularly helpful for logistic regression. Advanced ensemble methods for logistic regression often leverage different scaling approaches for different feature subsets to improve overall performance. Here we see a practical example of gradient descent optimization with polynomial features. Proper scaling is essential when using higher-order features like this. Let's summarize the key benefits of data scaling in logistic regression. When implementing data scaling, there are important technical considerations to keep in mind. Always remember to apply the same scaling transformation to your test data that you applied to your training data. Future trends in logistic regression involve combining it with other machine learning algorithms to create more powerful predictive models. Hybrid models aim to overcome the limitations of single algorithms. By combining logistic regression with other techniques, we can capture complex nonlinear relationships, improve prediction accuracy, and reduce overfitting. Logistic regression and decision trees have complementary strengths. Logistic regression provides reliable probability estimates and works efficiently with limited data. Decision trees, on the other hand, excel at capturing nonlinear relationships and feature interactions. Combining these approaches creates models that leverage both sets of advantages. Neural networks can be combined with logistic regression to create powerful hybrid models. The neural network layers extract complex features from raw data, while the logistic regression component provides interpretable outputs and probabilities. This approach maintains interpretability while leveraging deep learning capabilities. Stacking is a powerful ensemble technique where multiple models feed their predictions into a meta-learner. Logistic regression is frequently used as this meta-model due to its interpretability and probabilistic output. This approach combines the strengths of diverse algorithms while reducing model-specific biases, leading to improved overall performance. Hybrid models must be carefully integrated into the full predictive modeling cycle. This includes proper data preparation, thorough evaluation, and ongoing monitoring. The complexity of hybrid approaches requires rigorous validation to ensure that improvements in performance justify the added complexity. Hybrid logistic regression models are already finding applications across industries. In healthcare, tree-boosted logistic models improve patient risk prediction. Financial institutions use neural-enhanced logistic regression for credit scoring. Marketing teams leverage ensemble techniques to better predict customer behavior. These real-world implementations demonstrate the practical benefits of hybrid approaches. Future research in hybrid logistic regression will focus on several key areas. Automated model selection will streamline the development of hybrid approaches. Optimization of ensemble weights will maximize performance through precise model combination. Explainability techniques will make complex hybrid models more transparent, and adaptive systems will enable real-time adjustments to model combinations. The equation shown here represents how different models can be weighted in an ensemble.